Team Foxtrot, a student-led drone manufacturing team from the esteemed corridors of Ghulam Khan Institute, Pakistan. Our latest endeavor, Project Spectre, is our unmanned aerial system designed for the SUAS 2024 challenge, crafted to excel in payload delivery and precision surveillance to aid in the mission challenges. Our development team comprises of over 50 students, divided into multiple sub-teams including design, automation, fabrication, software development, documentation, and media. Together, we've pooled our expertise to bring Spectre to life. Here's a glimpse of our flight team, a group of 11 individuals.
Requirements and acceptance criteria. Project Spectre has been carefully designed and thoroughly tested to meet SUAS requirements and earn the highest possible points. Project Spectre has a maximum takeoff mass of approximately 33 pounds, which is within the 55 pounds limit. Safety pilot and GCS have been deployed according to challenge requirements. LiDARs are used for obstacle avoidance, continuously monitoring the surroundings to execute evasive maneuvers as necessary. Electronics and payload are well secured on the UAV to avoid any debris falling during the mission. 20 test flights were performed, and the maximum waypoint deviation was 10%, which is within the allowed limit. Using two 30,000 mAh 6S batteries, the drone has a total flight time of approximately 40 minutes and can go more than 10 miles on a single flight. 104.1 pound force of total motor thrust, approximately 26 pound force from each motor, is enough to carry the UAV to an altitude of at least 75 feet. System overview. Our UAV is based on a modified H-frame quadcopter. It is propelled by 4 Hobbywing X6 Plus motors with 24-inch propellers. Powering all systems are two 30 Ah 6S batteries in series, providing a thrust-to-weight ratio of 3.15 and a top speed of 49.2 feet per second, with a maximum takeoff mass of 33 pounds. For autonomous navigation and control, we used a Ishaq V6X flight management unit in conjunction with a Neo 3 GPS module. Mission Planner software acts as our ground control station, monitoring critical flight parameters in real time, including battery voltage, airspeed, altitude, satellite count, and heading. Object detection, classification, localization, and mapping tasks are managed using a Turret T10X Pro camera with feed processing handled by NVIDIA Jetson Orin Nano. To enhance safety and facilitate obstacle avoidance, our UAV is equipped with Benawake TF Mini S LiDARs, each offering a detection range of 8 meters. For communication between ground control and autopilot, we rely on a Radiomaster TX16S transmitter, having a frequency of 2.4 GHz along with an RFD 900A telemetry, which operates at 915 MHz. High-gain antennas are integrated to extend the telemetry range, ensuring reliable data transmission over distances of up to about 24.85 miles. Imaging ODLC design and testing. Equipment overview. Our drone is equipped with a Turret T10X Pro camera featuring a 3-axis gimbal for stable footage capture and 10x optical zoom capability. It records videos at 1080p 60 fps and transmits them via HDMI 1.4 port to the NVIDIA Jetson Orin Nano for real-time computer vision processing. Camera specifications. The camera has a focal length ranging from 0.4 inches to 11.8 inches, with an image sensor size of 0.19 by 0.14 inches. The video resolution is 1920 by 1080 pixels, providing a 16:9 aspect ratio. Considering the aspect ratio, the effective sensor size for video becomes 0.19 by 0.11 inches. Coverage area calculation. At a working distance of 82 feet and using the maximum focal length, our video frame of 1920 by 1080 pixels covers an area of 1.3 by 0.74 feet on the ground. This calculation ensures precise coverage and resolution for our footage. Resolution and object detection. With the calculated parameters, our camera can resolve objects as small as 0.71 by 0.92 feet, ensuring high-quality imaging for object detection tasks. Algorithm and processing. The YOLO V5 detection model was trained to detect colored shapes and emergent objects in the captured footage. Additionally, optical character recognition techniques are employed for letter identification. YOLO V5 will also be used to determine the color of the shape. Integration with drone control. Python's DroneKit library was used, which facilitates seamless integration between the drone's movement control and payload mechanism upon object detection, enabling automated responses based on identified objects. By leveraging these components and techniques, our drone is equipped for efficient image classification and object detection tasks, ensuring accurate and timely responses to detected objects in its environment. Airdrop design and testing. Our airdrops are standard 8-ounce bottles that are to be dropped safely to the ground. The custom-designed payload housing was printed using FDM 3D printing and ABS material. Non-load-bearing surfaces were hollowed out to save weight, material, and other resources. A rope mechanism was chosen to safely drop the bottles in the target area. The payload mechanism has a capacity of 2 bottles at a time. The bottle is freely suspended to a servo control rod using a string. A second string is attached to the bottle and wrapped around a freely rotating rod. Upon release of the rod from the servo, its drop is slowed down due to friction from the bearings. This ensures the bottle lands without any damage. The length of the second string is shorter than our standard drop-in height. This eliminates the need for a rope cutting mechanism and ensures stability for the UAV when the bottle is dropped. In total, 35 tests were performed to evaluate the performance of the payload delivery system. We tested the rope mechanism with and without attaching it to the UAV to ensure proper working. The tests were conducted at the standard height of 80 feet above ground level, which is more than the minimum height of 75 feet above ground level mentioned in the rules. Out of the 35 drops, 31 were successful. 5 tests were conducted without connecting the payload dropping mechanism to the UAV, of which 4 were successful. With the mechanism connected to the UAV, 26 of the 30 drop tests were successful. The drop accuracy of the system was found to be 88.6%. Our tests resulted in an average drop time of 8.3 seconds. Communication design and testing. We make use of Mission Planner as our GCS to set up the automated mission and its configuration. Real-time data monitoring, flight path control, calibration, fail-safes, and sensors are also controlled through Mission Planner. Moreover, to acquire real-time data from the UAV such as the airspeed, battery voltage, and other critical parameters, a long-range RFD 900A telemetry is used, which operates at 915 MHz and has a maximum range of 24.85 miles. Its transmitter is designed with a low noise amplifier for waves with an amplitude of less than 20 decibels along with a low pass filter to optimize its functionality. All of this combines with its dual antenna interface to support diversity and allow accurate transmission of data over long distances. Our Radio Master TX16S Mark II 4-in-1 radio is being used for flight control and controlling other mechanisms. It operates at a frequency of 2.4 GHz, which is permitted in the US and has up to 16 channels with multiple transmitter modules and gimbals for center point positioning and temperature stability. Communication performance. Our UAS uses a telemetry system that has a frequency range of 902 to 928 MHz, allowing us to transmit and receive data efficiently. The system has over-the-air data rates of up to 250 kilobits per second, which enables us to transfer large amounts of data quickly. With this system in place, there is an expected packet loss of less than 1%. The CUAV V6X flight controller uses its built-in sensors and Neo 3 GPS to control the motors to fly according to the stored mission plan. Upon detection of the airdrop markers, it is directed to actuate the payload servo by the drone kit library running on Jetson or in Nano. It also sends data to GCS through telemetry and receives radio signals from the pilot in case of manual override. Aircraft design and testing. Airframe. An edge configuration quadcopter was chosen for the competition with an airframe size of 45 inches. The design approach was to maximize the strength-to-weight ratio to result in as little maximum takeoff mass as possible. Thus, the quadcopter arms are composed of 25 by 2 mm carbon fiber tubes, providing adequate flexure strength while saving on weight. PVC T-joints were used to connect central booms to motor arms, given their easy availability and replacement in addition to sufficient strength. The center plate and battery plates are made from 0.06-inch thick aluminum sheet, allowing accessibility to electronics and ease of manufacturing. The sheet thickness was chosen by using a computer code to iterate over available options to find one that could bear the expected loads while providing the highest strength-to-weight ratio. Previous experience has shown boom connectors to be the most frequent point of failure during a flight or in case of a crash in a multicopter. Thus, aluminium boom connectors were used as to offer superior strength to any 3D printed plastic connectors. The custom-designed payload mechanism was printed using FDM 3D printing and ABS material. Non-load bearing surfaces were hollowed out to save weight, material, and other resources. Propulsion system. After considering the maximum takeoff mass and the speed required for the mission, 4 Hobbywing X6 Plus brushless DC motors were selected. When paired with a 24-inch diameter 8-degree pitch carbon fiber propeller, each motor can provide a maximum thrust of 26.02 pound-force, giving a thrust-to-weight ratio of 3.15. The motors work on a 12S configuration and have built-in ESCs that can withstand a maximum current of 100 amps. The power supply system consists of two 6S 30,000 mAh batteries from T-drones, connected in series. This will allow us to fly for 20 minutes total before having to land and swap the system for 2 identical batteries in the same configuration. Therefore, our UAS has a total flight time of 40 minutes and the estimated maximum speed is 49.2 feet per second. In total, 9 full-length 12-mile test flights were performed to assess aircraft performance. PID values were adjusted to maximize waypoint accuracy. 32 test flights over 415 minutes covered 480 waypoints with a recorded maximum deviation of 2 feet. A geofence was set up to prevent the UAV from crossing mission flight boundary or flying above 400 feet. Tests conducted showed an above 95% success rate for both cases.
Autopilot design and testing. For the flight controller, CUAV Pixhawk V6X is being utilized as the core for the autonomous flight. It has a newly built-in shock absorption design which minimizes vibrations due to shocks, thus providing better stability to withstand harsh maneuvers. Having a double precision STM32 processor and high-performance ARM M3 core processor provides the drone with significant computing power, allowing for complex flight algorithms and real-time data processing. Thus, the Autopilot integrates with multiple sensors including accelerometers, gyros, magnetometers, barometers, and GPS, enabling accurate flight stabilization and navigation. The flight controller comes with Neo 3 GPS, which is an industrial-grade compass, barometer, and safety switch all in one, offering improved coverage and reliability in challenging environments. The Neo 3 GPS module features a high update rate and low latency, suitable for dynamic UAV flight operations, including waypoint navigation, geofencing, and return-to-home functions. The CUAV flight controller is compatible with various ground control stations and telemetry systems, facilitating seamless communication and control during flight operations. Mission Planner is used as a ground control station to help with composing the autonomous flight path. During the flight, it records and displays critical flight data such as altitude, airspeed, satellites count, and battery voltage in real time. Mission Planner also allows the user to perform calibrations on sensors such as the accelerometer and GPS, as well as calibrate various failsafes easily. It can also track features like EKF, which is useful to detect any malfunctioning equipment. A total of 20 flights were conducted, which lasted 290 minutes. Testing revealed that Spectre successfully flew through 472 out of 480 delegated waypoints, giving a waypoint navigation accuracy of 98.3%, while attaining a maximum height of 400 feet. The maximum deviation from waypoints was of 2 feet. In addition, 12 flights were conducted to test 6 failsafes, lasting a total of 130 minutes. 2 flights were conducted for each failsafe and a 98% success rate was achieved as a result. Obstacle avoidance design and testing. Our obstacle avoidance system incorporates Benevik TF Mini S LiDAR sensors positioned at each rod of the quadcopter to minimize blind spots. These LiDARs interface with the flight controller via the I2C port, utilizing Autopilot's bendy ruler algorithm to detect obstacles. The algorithm scans the surrounding area, identifying open spaces and determining a safe path to navigate while maintaining the course towards the destination. Before decision making, data collected from the LiDARs undergoes rigorous processing. This involves filtering, fusion, and analysis to generate a comprehensive situational awareness model. Machine learning algorithms are employed to interpret this data and make informed decisions regarding obstacle avoidance and flight path optimization. The testing procedures encompass a comprehensive evaluation of obstacle avoidance capabilities under various scenarios. Static obstacles were first created virtually in Mission Planner, and later testing was conducted on real objects. Out of 15 tests, 12 were successful. Moreover, Spectre avoided 27 out of 30 dynamic obstacles. The result of these tests has demonstrated the efficacy of our obstacle avoidance system in navigating complex environments while maintaining course accuracy and ensuring mission success. Alternatives considered. During the initial design phase for SUAS 2024, several options were considered that met our requirements. These included fixed wing, hybrid VTOL, quadcopter, and hexacopter configurations. A fixed wing offers longer flight times, a higher cruise speed, and larger payload capacity. However, its inability to hover leads to lower accuracy during object detection and payload delivery, necessitating the use of a more expensive camera. A multi-copter configuration provides the ability to hover in place, making it ideal for object detection and payload delivery. Both a hexacopter and a quadcopter configuration were considered. The hexacopter configuration provided greater component redundancy compared to a quadcopter. However, the benefit was not worth the extra energy consumption and additional component costs. A hybrid VTOL configuration provides the benefits of both a fixed-wing aircraft and a multi-copter. However, it poses additional complexity associated with fabrication. Moreover, considering the weather conditions and the required hover time in our mission, a hybrid VTOL would be very unstable in operation. So, the advantages of a hybrid VTOL configuration failed to outweigh the risks associated with it. For these reasons, a quadcopter configuration was finalized. For our payload dropping mechanism, we considered both a rope mechanism and a parachute delivery system. The parachute delivery system would have a shorter drop time but was found to have lower accuracy, had an associated risks of steering away from its course due to wind gusts, and had greater design complexity. Compared to this, the rope mechanism had higher accuracy and ease of retrieval of the payload, making it a clear choice for our system. Safety, risks, and mitigations. A flight termination system has been incorporated with a return to land response after 30 seconds of communications loss. Wire connections are properly soldered and covered with heat shrinks to prevent short circuits that could lead to a fire. Batteries are transported in LiPo bags, and high quality battery chargers are used to minimize the risk of outbursts, while battery monitors are used to monitor any excessive current drawn from batteries and take prompt actions. Cooling fans with acrylic casing are used to prevent overheating of processing components, that is, Jetson or in Nano. A safety switch is used to prevent motors from starting by mistake until it is armed using mission planner or remote control. Digital servos prevent malfunction, provide the required torque, and avoid any slippage. Nylon insert lock nut fasteners are used. They have blue nylon rings inside them that create friction with the bolts and keep the nuts from coming loose due to vibrations or other movements. The use of washers in drone assembly allows for load distribution, alignment, and reduction in vibrations. Aluminium boom connectors chosen to prevent the parts failure during flight or in case of a crash. Full mission testing. All subsystems encompassing failsafes, imaging and ODLC, airdrop mechanism, communications, aircraft, and obstacle avoidance systems underwent thorough individual testing alongside comprehensive full flight missions. A total number of flights were conducted, fixing system issues and conducting evaluations in the process. Communication was intentionally deactivated to assess the RTL failsafe feature after a 30-second interval in 6 flights. Aircraft was able to return to its home position in 100% of the time, ensuring the failsafe's reliability. To evaluate the aircraft's ODLC capabilities, 10 objects were strategically placed across a 194,000 square feet area for search operations. Across 15 flights, the team attained an 80% accuracy rate in object identification. The payload reliably landed within 20 feet of the target area around 90% of the time. The timeline maintained an average score of 100%, requiring 15 minutes for setup, 30 minutes for the mission, and 10 minutes for teardown. Spectre successfully navigated over 350 waypoints with a 99% accuracy rate and avoided 90% of obstacles encountered. Across various metrics, including a timeline score of 100%, 100% in failsafe, 80% in imaging and ODLC tasks, 90% in the airdrop task, 90% in the obstacle avoidance, and 100% in autonomous flight, the team achieved an overall average score of 93%. Summary. To sum up, Project Spectre has been thoroughly engineered and tested to meet SUAS 2024's challenges. It can fly more than 10 miles on a single charge with payload, can detect ground markers with 80% confidence, and can avoid mid-air collision with a 90% confidence thanks to its slider system. With its minimalistic and task-centric design, we are adamant that it will perform well at the competition.